Hello, everyone, and welcome. I'm Rick Peterson from the ASA office. Thank you for joining us today for this presentation. Just a couple of quick notes. I encourage you to submit questions at any time during this presentation. We'll be leaving some time at the end for a Q&A session. But if you want to submit a question to the panelists, please do so using the Q&A feature as opposed to the chat feature. It's just easier for us to keep track of the questions that way. So that's all I needed to say. So I'll hand it over to the current chair of the Privacy and Confidentiality Committee, Saki, if you will.
Thanks, Rick. Welcome, everyone, on behalf of the Committee on Privacy and Confidentiality. Thanks for joining us today. We have 3 speakers and 1 hour, so in the interest of time, I'm going to be very brief. I do encourage you to visit our website, which is up here on the slides. On that page, you can find the webinar flyer, which includes all of the abstracts as well as the bio sketches. And after the webinar, you'll be able to find the slides from the webinar as well as a recording. So let's jump right in. Our first speaker is Brett Boiler-Jones from Harvard. He's speaking on the potential of privacy-preserving generative deep neural networks to support clinical data sharing.
Great, thank you, Saki. Let me just go to full screen. Does that look okay?
Looks great.
Perfect. All right. Well, thank you very much for having me. I'm excited to talk about this topic. It's largely based on a paper that we published, but we'll try to provide some sort of motivation and future directions and sort of the current state of the field as well. And so we really set out to ask the question, can we share clinical data without sacrificing privacy? This is a huge challenge around clinical data because there are a lot of sort of initial analyses that we'd like to do that require very intensive legal processes to set up DUAs and other sort of agreements across institutions, which frankly, oftentimes are enough friction that they don't end up happening. And so our goal was to try to ease this initial sort of early set of analyses to then see if it's worth actually setting up the DUAs and going through sort of all of those costs to the institutions. And so to provide a little bit of motivation, some of the community may be sort of familiar with this sort of back in the sort of 2000s, there was a period where Netflix did an original prize and then had announced a second prize around making recommendations to their users. They had to cancel the second one largely for legal liability when it came out that a group showed that given a certain number of movies, you could actually potentially re-identify whether somebody was in the actual data set or not. And so this led to Netflix sort of canceling this competition. And the reason I bring this up is to sort of make the point that just because somebody is de-identified doesn't mean that they're anonymous, and we need to be very clear about the separation. Another sort of great example of this was back in the 1990s when the state of Massachusetts tried to release anonymous healthcare data. This is sort of another famous example where Latanya Sweeney, who I believe now is at MIT, showed that she could re-identify people within the data set using very few features and eventually mailed the governor's health records to him to sort of prove that point and sort of illustrate that this was a risky endeavor. And so given sort of this motivation, we don't want these to be reasons to sort of slow progress around things like reanalysis of clinical trials and other things that are really important to understand how we can improve healthcare. And so one such example is when the New England Journal sponsored a program where they actually released this particular clinical trial data set called the SPRINT trial, which was a trial to study whether more intensive management of hypertension was worth it, essentially whether it was worth continuing to add hypertension meds until you could get people into a reasonable range, sort of beyond the typical standards of setting the number of medications. And so with this, we use this as sort of the base data set. It was a particularly interesting data set because at the time, there's a large discussion over the idea, many of you may have heard, research parasites, and sort of whether or not secondary analysis of data was a credible exercise and everything else. And I think we fall sort of firmly on the idea that sort of getting data into people's hands to do these secondary analysis is really important. And so we use this as sort of a test data set to say, is this possible? And so even though this was a endeavor to release data to a wider audience and for it to be public, and the fact that it was fully de-identified, it did still require IRB approval, even though I think oftentimes this would be considered exempt and not human subjects research, given the fact that it is de-identified historical data, and a DUA signed by both you and your institution. And for those of you at major institutions, this involves going to sort of your signing official who has the magic pen who can actually sign these agreements, and obviously can take quite a while because of that. And so to do this, we wanted to say, can we take in this clinical trial data and actually train a model that would generate synthetic data that was realistic enough that it could be useful, at least for an initial set of analyses. And so we chose to use generative adversarial networks. This is sort of the very basic premise where there's really two important components to, again, the first is that we have a generative model that is trying to sort of learn the distribution and generate realistic samples, and a discriminator, which is trying to tell whether a sample is from this synthetic generator or actually a member of the real data set. And by sort of iterating on this process, you can learn to generate better and better samples and actually learn the distribution of the data. And so this figure is sort of going back to the original presentation of GANs, where this dotted blue line is the discriminator, so it's trying to draw a boundary between the white dotted points, which are the real data distribution, and the yellow line, which are which is the generator's distribution. So you see over time, it becomes harder and harder to differentiate the two groups, and the generator is learning the relative distribution of the data. There are obviously challenges with this, but it's shown some pretty incredible results where initially we've seen a lot of work in images. This is back in 2018, and so this is now sort of old and not sort of the state of the art, but you can see pretty realistic faces being generated. And so with that, there were other improvements where now there's the question of, could we actually add an additional task to the GAN where we can put in a class label for a particular data point and actually try to generate a member of that class. And so now the discriminator has to not only try to tell if something's real or simulated, but also predict which class something is meant to be in. And so you do that same sort of mini-max process to iterate over and improve the training of both the generator and the discriminator, and you can generate more and more realistic samples. And so again, if we go back to sort of 2016, I show this to hopefully show the progression of the field, where this was the original paper showing that we could generate images of particular classes. In these cases, you can see that they're fairly blurry, low resolution, all sorts of challenges, but you can generally see that it's trying to generate flowers here and birds here. Over time, these have gotten much better, and we are able to sort of create examples to our own liking by moving through the latent space and sort of choosing how we want a car to be laid out and what the background should actually be. And so now there's a lot more control, and we've learned a lot about how we can actually move through the latent space to generate examples that we're interested in. Again, this is another sort of more recent paper where you can take sort of general ideas now and generate very realistic looking images. And so it's a field that I think has come very far in less than 5 years or so. And so I show all of this to say, these are really cool technologies. And we asked the question, could we actually use this to generate clinical trial data? And I think initially we saw, yes, you could generate sort of realistic patient trajectories. This is just looking at systolic blood pressures over time and sort of comparing them between the two groups with averages, just to show sort of, hey, you can have these trajectories. There's other factors that are being generated as part of the trial. But it's sort of close enough from an initial perspective that we said, hey, this is interesting. Let's sort of pursue this further and see what we can do. And so now we have some synthetic data that we don't know if it's useful or not. But we said, what could we actually do with this? And one of the first things we had to actually think about is, just because we've generated this with a GAN doesn't mean that it's actually private. And so as we were sort of looking at the synthetic data generation field and sort of some of the things that had improved there. The other field in terms of understanding when there are risks in these processes was also moving forward. And I think this is one of the more interesting examples where this group actually did membership inference attacks, where they could figure out if an individual was part of the training data set or not, just by looking at different shopping APIs that were available. So these are APIs provided by Amazon and Google. And so they don't ever actually even see the data generation, data generating model. They're just using the API for this. And so obviously what this told us was that just because you have synthetic data doesn't mean that it doesn't reveal information about the underlying data source and who's in the actual training data. And so to answer this question, we were lucky. We were at Penn at the time. Erin Roth, who is sort of one of the leaders and sort of, I think, sort of key figures in differential privacy, was there and introduced us to one of his grad students, Stephen Wu, who was very talented in this area, and said, hey, we could introduce differential privacy to the process to enforce constraints and give us realistic bounds of what sort of privacy loss would be expected under different parameter settings. And so the core sort of principle here is that we can't fully anonymize data and have it remain useful. There's a trade-off there that we have to weigh in this process. But we can offer mathematical guarantees of the likelihood that somebody could actually determine whether a subject is in the data set. And so to give sort of a very, very high level in this very short talk of sort of what differential privacy actually looks like is, if we are asked the audience the answer of a question, and before they actually give us their answer, everybody flips a coin. And if it's tails, they actually give us the real answer. If it's heads, they give us a random answer. We now have a situation where each individual person can plausibly deny that they gave either a real or fake answer. And therefore it's impossible. It becomes harder and harder to tell who's actually a member of the data set and is answering the question. And so obviously we wouldn't in practice likely make it 50-50 in terms of flipping the coin, because that would hurt sort of signal in the answer and you need a huge sample set. But it does, I think, start to illustrate the point of how you actually create privacy in this way. And so to do this in the context of, again, what we really needed to realize is that there's only one aspect that is touching the real data. And one of the sort of really cool properties of differential privacy is that downstream analyses all maintain sort of the same properties, and they're robust based off of sort of the implementation of differential privacy upstream. And so to do this, we only needed the discriminator to be differentially private. And the way that this actually works in practice is that we can essentially limit the gradient for any given step so that we know the appropriate amount of noise to add as we're actually training the discriminator model. And so this is something that, funnily enough, within the sort of deep learning community is tried in some ways to try to encourage models to generalize. So adding some level of noise to individual gradients, in some cases can help with model generalization. And so it actually meshes sort of well where we can add differential privacy to the discriminator, and then, by nature, then have robust synthetic data trained under differential privacy. And when you do this in practice, training these models is not necessarily easy. Training GANs is not necessarily easy by itself. I think the field has come a long way, but this was sort of some of our initial figures where you see the purple lines generating generated by the private model. And again, for time's sake, I won't get into sort of what we did, but by a number of sort of simple tricks, we could actually help to generate more and more realistic samples. One of the keys being to actually ensemble across epochs of training to get rid of areas where the noise outweighed the actual signal. And so this led us to two other quick questions, which I'll just touch on, which are now these private data actually useful? And so to test this, we could say, let's take the real data and actually train models that are trying to perform a particular task. Let's take the public synthetic data, so the data that are not trained under privacy, and ask how they do on a particular task. And then let's try to do the same task where we are using the data that were generated under differential privacy. And when we do this, we saw that the data were realistic enough for a variety of tasks that we do see some drop off from the sort of real benchmark that's sort of to be expected. But in some cases, we actually saw that the private models were doing as well or even better than the non-private models. And again, this goes back to potentially asking questions about generalization. We also then put these patients in front of clinicians and sort of compared the two distributions and asked the question of whether real people, so in this case, internal medicine docs with specialties in hypertension management, whether they could see whether somebody was a real person or a synthetic patient based off of their prescription patterns over time and the way that their blood pressure reacted to that. And what we saw is that they had a lot of trouble differentiating these two groups. And so with that, I'll sort of just mention, this is now originally going back to our training of GANs all the way back in 2017, where GANs were pretty challenging to train. There weren't a lot of methods for neural networks to handle mixed data. There were lots of challenges around the number of samples, and that will always be a problem with clinical data. But it's a field where things have come a long way. There are tons of methods even in the last couple of years that have improved training of GANs, as well as models that have done things like being geared at time series specifically, which may have been better in our particular example, or dealing with mixed data types, and even allowing you to explicitly sort of model a particular correlation structure that you care about for downstream learnings. And so all of this is to say, we think there's a lot of potential here for sort of feasibility studies and ways to get data into people who are very interested in doing secondary analysis hands early, and then as soon as you have something promising, then you can go through the effort of setting up DUAs and everything else in place to sort of validate in the real data set. And so with that, I'd like to thank a number of contributors, particularly Casey Green and Jason Moore, who are my PhD mentors. Casey was my primary mentor on this particular paper, and then Erin Roth and especially Stephen Wu, who is a co-author and really our differential privacy specialist for this work. I should mention that Chris Williams was a high school student at the time who also contributed significantly to this work and is a co-author on the paper. And so with that, I'd like to thank everybody for their attention, and I'd be happy to answer questions, I think, at the end of the other talks as well. Thank you.
Thank you, Brett, and for sticking to your time exactly. Monica, you can go ahead and share your screen and speak right away so we know you have sound.
Thank you, Saki.
Great, we can hear you great.
Sounds good.
As a reminder, yes, you can enter your questions in the Q&A and questions will be addressed at the end.
Thank you, Saki, and thank you, Brett, for a wonderful talk. And I'm really happy and honored to be one of the presenters today for ASA Privacy Day 2022. My name is Monica, who I work at Vassar College, and I'm here to introduce you a concept and a new methodology about synthetic data, in particular, how to incorporate disclosure risk when you're designing your data synthesis models. This is joint work with Terence Savitsky from the Bureau of Labor Statistics and Matthew Williams from RTI International. And the work itself was supported by the ASA NSF-BLS Fellowship a few years back. Oops. All right, so many of you might be wondering, oh, can we ever get high utility and low risk synthetic data sets so we're able to use it for public release as well as any kind of analysis you want to do? The short answer is unfortunately no, due to what we call a utility risk trade-off of synthetic data. So what we mean by that, on the right-hand side, I share with you a illustration.
Excuse me, Monica. We're still on your first slide. I think maybe the issue might be if you were sharing your screen as opposed to sharing your application. Did you want to change that up?
Yeah, sorry about that. So let me try it again. Sorry about this. And I'm trying to, yeah, so I'm sharing. What about this one?
Okay, we see your PowerPoint. Did you want to go? Okay, that's perfect. We can see you transition the slides. Did you want to go through to a full screen mode?
Yeah, let me give it a try because that's what I did before.
That's perfect.
Okay, awesome. Thank you so much. So already, so we're here talking about the utility risk trade-off of synthetic data. So the story I want to tell over here is that even though ideally people really want to have synthetic data with high utility as well as very low disclosure risks, but usually wouldn't happen in this happy world because of this, what we call utility risk trade-off of synthetic data. To illustrate the idea, on the right-hand side, you can see we have 4 different synthesis models being applied to a sample of the consumer expenditure surveys, which is coming from the Bureau of Labor Statistics. And notice that here we plot the utility on the x-axis and the risk on the y-axis. So we're trying to show you the 2-dimension idea. And then, of course, the higher the utility, the closer to the right-hand side, and higher the risk, the closer to the top. And another caveat over here I want to mention is that because usually people simulate and release multiple synthetic data sets to capture the variability. So that's why we are designing this illustration with what we call a 2-dimensional box plot. But you can see that we're trying to capture the variability across the different synthetic data sets. So the general idea over here, as you can see, is that for synthesizer 1, or this first synthesis model being applied for the same data set, it seems to have very high utility, but unfortunately very high risk as well. And then for another or 3 other synthetic synthesis model, for example, the synthesize 4, this is the case that, well, unfortunately, you don't have as much high utility, but at the same time, you don't have as much high risk as well. So this is a well-known phenomenon called utility risk trade-off. And for us, the goal here is that what if I got a synthetic data set that is really, really nice in terms of high utility, but the risk is a little bit too high as well that I don't feel comfortable releasing. So we're trying to answer this question using what we're proposing over here. So for example, when you encounter that kind of situation, usually agencies or data holders, they might want to design 1 or more data synthesis models to reduce the synthetic data risk. But at the same time, as we know about the trade-off, it will also result in lower utility. So for example, if I really want to have a desirable balance between utility and risk for my consumer expenditure survey sample, so maybe instead of choosing synthesizer 1 or synthesize 4, which is at the 2 extremes, maybe I will strike a balance and choose 2 or 3, for example. So this can be a little bit tedious to do, meaning that every time if I'm not happy about my risk, I kind of have to go ahead and design a new synthesizer and hope for the best. I will be able to reduce the risks, at the same time reduce a little bit of the utility. So to avoid designing new synthesis models every time when the risk is too high, we are proposing a method trying to incorporate the risk in an existing synthesis model that you already like, and we try to use that to provide higher privacy protection. So the particular way that we're doing it is what the talk title is trying to say is we're trying to incorporate the risk in the synthesis model. And in particular, we're going to incorporate it as a weight in the likelihood function of the synthesis model. So to get started, we're going to first of all define risk as a probability between 0 and 1, meaning that when you have a higher risk, your risk evaluation value is going to be closer to 1 and vice versa. Intuitively, any record with really high risk, meaning that the risk measure is closer to 1, we wanted to give more privacy protection for it. And in order to do that, we're going to reduce those high risk records likelihood contribution with what we call a low weight to provide more privacy protection. In a sense, you can imagine that in the confidential data distribution, you can have a high risk portion, and we're trying to smooth that portion in order to provide higher privacy protection for those records in that particular area. So this is a general idea. Mathematically, we are introducing you here in the bracket, that's the joint likelihood of all of the n observations. And then outside of the bracket over here, this is the prior distribution in any Bayesian model. So in the bracket, what I want to highlight is that also, first of all, we have theta as the model parameters, gamma as the model hyperparameters. So outside, this is the prior. And inside in the bracket, we have each likelihood contribution of the yi observation given its parameters. And you see that we raise it to what we call a weight called alpha I. And that is the way that we can be calculating based on the risk of the record. Specifically, we have the weight of record I to be 1 minus the risk of record I. So remember, the risk itself we define as a probability. So alpha I, the weights themselves, going to be also between 0 and 1. And more importantly, we do this inversely proportional in a sense that if I have a high risk record, saying that my risk of record I is closer to 1, then my weight going to be very close to 0 because I'm using 1 minus that risk. So if I look at the expression over here, the alpha I going to be closer to 0, meaning that the likelihood contribution of this record going to be reduced to minimum, almost like none. Okay. On the other hand, if I have a low risk record, let's just say my risk I is very close to 0, I'm going to have a weight that is going to be closer to 1. And if you look at the equation one more time, in that case, we're going to have a high contribution or close to 1 contribution of my likelihood contribution of the record I. So specifically, I want to mention that this kind of setup works with any Bayesian synthesis model, meaning that as long as you have whatever the density model that you have, you will always be able to raise it, exponentiate with the weight that we're going to design. And the weight, once again, is inversely proportional to the risk of each record. So with that in mind, I want to show you 2 illustrative examples so you know what we're trying to do intuitively. So here on the right-hand side, I plot I guess here is the scatter plot of the risk of the record against the outcome value, like say yi of that record. Whereas at the bottom, I plot the weight against the outcome value of the record. So basically, we're going to look at 2 special cases, okay, the red dot here and the blue dot here, to see how the weighting come out in terms of how we can design the risk in the synthesis model. So if we start with the blue dot over here, this is the case, if you can see, which is having relatively high risk, because the risk, again, goes from 0 to 1. The higher the value, the higher the risk. So the blue one is an example of high risk, about 0.75. And in that case, if you remember, we use 1 minus that risk to get the weight, alpha I, for that record. So down at the bottom, we're going to get something closer to 0.25 for the weight. Okay, so that is the example of high risk to start with. So we're going to get a low weight for this record. And because of the contribution and the setup that we're doing, the exponentiation of the likelihood contribution with the weight itself, with a smaller alpha I, like roughly 0.25, we're going to have a reduced or less likelihood contribution of this particular record to the general synthesis model. And because of that, because of the smoothing that we're able to provide, we're going to provide higher privacy protection for that record. On the other hand, for the red dot that we have over here, so this is an example that the record started off with relatively low risk, okay? And then because of the inverse proportionality that we do, we have a relatively high weight, let's just say about 0.75 over here for this record. So for low risk, we're going to produce a high weight. And then in the construction, the contribution of this record to the joint likelihood will still be very high. Okay? And another thing I want to mention on this graph is you can see that we also added a dashed, yellowish or orange-ish at the top of the weight equals to 1. And that is the case that we don't do any kind of weight. So imagine that alpha I all of a sudden goes away, then that will just be a regular Bayesian synthesis model. And then that is every contribution, every observation contributes to the likelihood as is, because alpha I equals to 1. And then that represents the regular, what we call unweighted synthesis model. And then what we're proposing is the weighted synthesis model that we're able to incorporate the risk in the synthesis steps. So with that in mind, I want to show you our application to synthesize a sensitive family income information from the consumer expenditure surveys. And the synthesis model we use is a finite mixture model. But like I said, the particular construction that we have over here works with any Bayesian model. For us, we choose the finite mixture because it works really well when we have a high utility to start with for the original synthetic data that we're able to generate. And then we're trying to provide more privacy protection in that case. So this graph is a violin plot of record level risk for all records in the CE sample, the consumer expenditure survey sample. And we have the confidential data results. We have the unweighted regular synthesizer. And we have what we propose, the weighted synthesizer, the 3 different panels. On the y-axis, we have the risk. And once again, this is the risk for each record. And we're doing a violin plot. So this is showing all of the records in terms of the risk. And also, the higher the value of risk, closer to 1, the higher the risk for a particular record. So at a first glance, we can see that the confidential data obviously has a lot of records with really high risk. If you look at the between 0.5 and 1, pretty much all of the records are within that range. If we just do a regular synthesizer, like the finite mixture model that we propose, we are getting this unweighted. And in terms of the risk, we can see a huge reduction already, not only in terms of the mean, right, but also in terms of the top. And then when we apply the weighted version that we propose, we can further reduce the general risk, the risk profile of every record in terms of the mean, as well as the tail. So we're better controlling the highest risk or the maximum risk that we are able to allow. And also almost every record get further down in terms of their risk profile. Okay? And then, just like I said at the very beginning, there's always this utility risk trade-off. So whenever we're trying to reduce the risk a little bit, we have to accept the fact that we also will have to a little bit reduce the utility as well. So I also want to show you the results to give you a full picture. These are two tables. One of them is about the average family income, and the other one, which is the outcome variable that we're trying to synthesize. And the bottom one is a regression coefficient using a few predictors when the outcome variable is the family income itself. So once again, we show the data. This is the confidential information, and then the unweighted regular synthesizer and the weighted synthesizer that we propose. In each, we provide the point estimate as well as the 95% confidence interval, and we're just trying to compare. So the gold standard is the closer to the data row, the better. And then clearly we can see that the unweighted, without doing any kind of weighting that we're introducing, will have a better utility in terms of point estimate, as well as the 95% confidence intervals, I think, for both of these quantities of interest. But overall, as we can see earlier, we have a huge reduction in terms of the risk. So it will then be the data disseminator and also the agencies to decide whether this kind of trade-off is acceptable. Okay, so overall, we're able to achieve reduced disclosure risk at the price of slightly lower the utility. And for us, the main thing we want to convey is that whenever you're having too high a risk to start with for a synthesizer, you don't need to try to design one or even more different synthesis models to make sure that you can get your balance. But rather, you can introduce what we call this weighting mechanism, weighting method, to incorporate the risk into the synthesis model. So eventually you can have a better trade-off between the utility and the risk of your resulted synthetic data. So to sum up, we're just trying to recommend you don't need to design new synthesis models every time when your risk is too high. We're proposing a very general framework to achieve desired utility risk trade-off balance. It works for any Bayesian synthesis model as long as you start with one that you really like, but then unfortunately it has high utility, but also high risk. You want to reduce the risk a little bit, you can introduce what we propose over here. And we also want to mention that we have a version of this weighting method satisfies what we call asymptotic differential privacy, which I'm happy to share if anybody's interested afterwards. So if anyone is interested about the weighting method, we have a couple of manuscripts. Anyone who is interested about the utility evaluation, there is a very good paper a couple of years back talking about how to evaluate synthetic data utility, and also the risk evaluation. We have a couple of resources out there, including a package for you to try it out if you want. And with that, thank you so much for attention. This is my contact info, and I will now pass it to Erin.
Thank you, Monica. Our next speaker is Erin Williams from Urban Institute, who is getting his slides up now, and he will be speaking on fully synthetic microdata for public policy analysis. Take it away.
Thank you. So just before I dive in, for anyone who doesn't know, the Urban Institute, we're a nonprofit, nonpartisan research institution in Washington, D.C., and we focus on social and economic policy research. So the types of data I'm going to talk about today are incredibly important to our mission. I am but one member on a much larger team that spans the Urban Institute working on this project. And we've also benefited from excellent collaboration with the IRS and other researchers across the country. So we're really grateful for all the assistance. Tax data are incredibly useful. The IRS Statistics of Income Division maintains data sets that are useful for all types of research. Some of that research can be very tax focused, what's the distribution of tax burdens? And some of that research can be totally not tax related at all. What are measures of economic mobility over time, for example? But tax data are incredibly sensitive. As many people here are probably aware, there have been evolving threats to data privacy and confidentiality over time. There's more third-party data, more computing power, and new methods. And the IRS is very serious about statistical disclosure control and takes these risks very seriously. One thing that means is that over time, they've released less data and less information, which is a problem for researchers. So our goal is to produce fully synthetic tax data with the same record layouts as IRS administrative data that protects the confidentiality of tax return information, may be used for statistically valid analysis for certain research purposes, and then may be used as training data to develop programs to run directly on the confidential data. So with those goals in mind, I'm going to outline sort of our general synthesis methodology, talk about the supplemental SynPuff, which is a product that we've already released in collaboration with the IRS, talk about SynPuff, which is a product we're currently developing, and then close by talking about a formally private validation server that could be paired with synthetic data. So the first thing is we're working entirely with fully synthetic data. What that means is if we have a confidential data set, say with 2 observations and 4 columns, when we create the synthetic data set, every single value in the data set is going to be imputed by some kind of model. And in fact, when we start, we're going to start with a bootstrap sample of one of these variables, which means there's no longer really a one-to-one mapping from any row in our synthetic data set to any row in the confidential data set. We do this with a sequential process. So our goal is to approximate the joint distribution of the tax return information, which we can do with a product of a sequence of conditional densities. What does this actually look like? It means that we train a bunch of models directly on the confidential data. And then when we go to create our synthetic data, we randomly sample with replacement, say sex, the first variable. And then we're going to model age conditional on sex. And then we're going to model wages conditional on age and sex, and continue this process all the way through to the final variable using all previously synthesized variables as predictors or potential predictors. Right now, we've mostly focused on using classification and regression trees, or CART. It's a non-parametric model that was developed in the 80s. We've also used random forests and some other machine learning models. These tree-based models are really great in that they work well with data that don't fit common distributions. They're really effective when you have variables with lots of zeros or lots of common values, which appear all the time in tax data for sort of tax law reasons. And they can also do a pretty good job of capturing complex nonlinear relationships between variables. So the models add some amount of prediction error to the synthetic data, but we're dealing with really sensitive data. So we have a process by which we add additional noise. So instead of using actual values imputed by these CART models, our synthetic values are draws from normal distributions, where the mean of that normal distribution is the value predicted by the CART model, and the variance is what we call percentile variance. It's the optimal bandwidth for a kernel density estimator with a Gaussian kernel of the confidential percentile to which our predicted value belongs. That's kind of a mouthful, there's a lot in there. The real takeaway is, if we predict a value that comes from a very dense part of the univariate distribution in the confidential data, we're not going to add that much noise. But if we're imputing a value that comes from a very sparse part of the confidential data, it's going to have a much larger variance, and we're going to add more noise. And the idea there is if those observations are coming from sparse parts of the distribution, they're probably more sensitive. This addition of extra noise and also just prediction error ends up creating a lot of issues for tax data. There's all types of constraints that exist within tax data because of laws. So imagine something like IRA contributions. Your maximum IRA contribution is dependent upon your income, your age, your marital status. And so even in a simple case like this, maybe we synthesize a value that's $13,000, which is impossible according to tax law. So we have code that enforces these constraints during the synthesis process to make sure that all the data we create conform to tax laws. All the syntheses that we do are with an R package that we created called tidy synthesis. We basically break all of the things that can go into a synthesis, the components of a synthesis, into different objects. So you can specify the visit sequence, which is the order of variables, the process for adding additional noise, what types of constraints you want to have and how you resolve them. You put all of these into one presynth object, and it's lazily evaluated, which means we haven't really done anything. You finally run this synthesize function, and then you can leave your computer for several or many hours because it takes a very long time to synthesize data. This is currently private, but we hope in the future to make this package open source. Okay, so now I'm going to talk about some of the things that we've done with this methodology. The first one is this supplemental SynPuff. It's data that was never ever released by the IRS before this. It's a file of individuals who did not file taxes and did not have an obligation to file taxes in 2012. So these are people for whom the IRS has some information from information returns, but they don't hit the filing threshold, and so they don't end up in other data sets. It's about 26,000 observations and 19 variables. We applied the methodology that I just outlined, and I'll share some of the results. So on something like means, here we have the original confidential mean in blue and the synthetic mean in yellow. And you can see across the 19 different variables, we do a pretty good job of recreating all the means. If we look at something like standard deviations, again, the confidential data in blue, the synthetic data in yellow, you see we do a pretty good job of recreating the standard deviations. There is one exception, and that's tax-exempt interest towards the bottom. This is a particularly challenging variable because it's almost entirely zeros. I think there's something like fewer than 30 non-zero values, and so it's proven very tough to recreate. Let's look at the linear relationships between variables in our data set. So this is basically taking a correlation matrix on the confidential data, correlation matrix on the synthetic data, and differencing the two. Values of 0 or near 0 are good. It means we're recreating the correlations. And you see we do a pretty good job, again, with the exception of tax-exempt interest, I think because of that sparsity issue. But all of that's great. I mean, the main thing these types of data are used for is something called tax microsimulation. So the idea is you want to get a data set that's representative of a population and then essentially run it through a souped up version of TurboTax. And so we run the data through a tax calculator. We have some of the results here, again, with the original confidential data in blue and the synthetic data in yellow. And you can see for things like the count of records by AGI group, the mean income tax by AGI group, the total income tax by AGI group, we do a pretty good job of recreating the properties of the confidential data. So the reason we started with that simpler data set is because we're trying to create a fully synthetic version of what the SOI calls the PUF. And this is a data set that has been released with traditional statistical disclosure methods, swapping, top coding, and the like up until now. So this is a file of tax records from 2012. It's about 265,000 observations and 207 variables. It comes from a stratified synthesis, and so the records have different weights depending upon which strata they come from. And there are incredibly complex relationships between the variables. So definitely a step up from the file that I was just discussing a second ago. We've got a lot more variables, so we can look at the means in a slightly different way. Here we have the confidential weighted mean on the x-axis and the synthetic weighted mean on the y-axis. Being on this 45-degree line is good. It means we're recreating the means. You can see for the means that most of them, we do a pretty good job of recreating the means. They're on that 45-degree line. With our current synthesis process, we have a much tougher time getting the standard deviations. You can see for a lot of the variables, we're on that 45-degree line, but there are some variables where we're really missing out on getting the standard deviation correct. If we also look at the differences between the correlation coefficients, we can see that they're highly peaked at 0, and most of the correlation differences are around that 0 area. So we think we're doing an okay job of recreating the linear relationships between variables. We can also look at our tax microsimulation results. This time, the confidential data are in salmon. The original PUF, so that's after it's gone through statistical, sort of traditional statistical disclosure control methods, is in green, and then our synthetic data are in blue. And so for something like AGI, which is a pretty complex calculation on the data, we do a pretty good job of recreating the confidential data. But when we look at something like income tax, which is another pretty complicated calculation on all of our variables, we do a good job everywhere except for in that top 1%. So we're having some type of issue, I think mostly with capital gains income, where we're overshooting on the income tax. So we definitely still have work to do with this synthetic data set. I'm going to close by talking about work that we've done on a formally private validation server. So the idea here is, don't the synthetic data sort of solve our data access issue? And the answer is yes, for the specific purposes that we build the synthetic data, the synthetic data are a great solution. So for tax microsimulation, it's perfect, right? But not quite. So for some types of statistical modeling, not specifically built into the synthesis, things like regression discontinuity design or regression kink design, which are common on tax data, the results from the synthetic data are less likely to yield statistically valid results. So, to kind of put things in their groups, with the synthetic data, we're basically trying to let people calculate any statistic on a noisy data set. It requires assumptions about the data generation process and assumptions about the threat model. With formal privacy in our validation server, we're trying to calculate noisy statistics directly on the confidential data. This is great because it gives us a formal privacy guarantee about sort of this worst case scenario. And it's also great because it gives us a privacy budget, which we can use to quantify sort of the amount of information released by the IRS across releases. But it's challenging because basically we're going to have to come up with a new method for every type of statistic we want to calculate on the confidential data. And I definitely think there's still a lot of work to be done there. What would this actually look like for a user? A researcher could take the synthetic data, create an analysis, create their code, test things out, and get to a point where they're happy with it. They could sit down at this validation server terminal, run their program that's been developed on the synthetic data, and get back noisy results and sort of a budget impact of running those results. There would be a budget, sort of a first budget that would be very generous because it would only be for unreleased analyses. So we're sort of bringing in some elements of a trusted researcher model here. The researcher could choose from those different analyses and request that certain ones are released. And that would count against this smaller second budget, which would have a smaller allotment. This is just sort of how we envision things, and it may change over time. So how far in are we this? This is like a multi-year project. So we've been working on a prototype validation server that focuses on pretty simple regression models, as well as a secure cloud-based data platform. In the future, we want to work on an extended sort of validation server that could handle more types of analyses. We think that pairing fully synthetic data with this sort of validation server would be a good fit. It would expand access to tax data, but it could also be a model that could be used to expand access to administrative data for research at the national level, the state level, and the local level. Cool. Thank you so much for your time today. This is one of the papers that talks about our synthesis methodology. We just released a couple of papers that talk about our sort of conception of this validation server. I think I'm more than happy to answer a couple of questions now, and you're also free to reach out to me on Twitter or at my email address at the Urban Institute. Thank you.
Thank you, Erin, and all of you for your talks. That's great. Monica has answered several questions in the Q&A chat already. Do you want to add anything, Monica?
Yeah, sure. Maybe just quickly, because I'm not sure if everybody else can see the Q&A questions and my responses, but I did notice a few questions about how we calculate the risk. I didn't get the chance to describe what it is, but for those of you who are interested, we calculated identification disclosure risk, measuring how likely it is for an intruder to correctly identify a record in the data set. And in that case, we do assume certain variables known to the intruder and all that. So a lot more detail in the paper if you want to check it out. But the takeaway message I would say is that we recommend the agencies or data holders to use whatever the practice that they usually have for their risk evaluation. And we recommend them to scale it into a probability like what we did in 0-1. So you're able to get the inverse weight given whatever the measure that you have in the first place. So you can always design your own, but then as long as you're able to turn it into a probability measure, you're able to design the weight, and then you can, what we did, weighting those high risk records lower, so you're able to provide higher privacy protection for those records. So I think that will be the only thing I want to address, Saki. Thank you.
Great. I believe everyone can see the Q&A and once they're answered. There is one more question for Erin. What is the magnitude of your data set? Is it realistic to get a fully synthetic data when you have a large number of variables, say thousands of them?
Yeah, it's a great and fair question. I mean, I think like on a simple level, it depends, right, on how complex the relationships are between the variables. You could imagine a pretty, like if each variable is pretty trivial and has like a clear relationship, you could go to thousands of variables. I don't think that's typically the case. I can say that when we're dealing with this data set that has 200 variables and the relationships are pretty complex, that it's really challenging. And we do in fact see that the errors kind of compound over time with this sequential approach. And so if we had to go any further than the 200 variables we have now, I'd probably be way more panicked than I am now. And if we had to go to 1,000 variables, I think it would be very problematic. It's a good question.
Are all of your 200 variables considered sensitive?
That's an interesting question. Our approach has been, yes, we're treating them as sensitive just because the source data are so sensitive.
Right. I think Neeraj's applications, a lot of times there were subjective responses, which is probably not the case with tax data. Let's stick with your talk. There's a question from Christine Wells. What about the analysis of subpopulations with synthetic data?
I mean, I have an R Markdown report that has like every single analysis that we could consider, where we compare the analysis on the confidential data and the synthetic data. And for the things that we can come up with, it works pretty well on the subpopulations. But that's like one of the challenges with synthetic data. You can't consider everything. And so then, how do you know if you've like drawn the analysis that doesn't work very well? And I think that's part of our motivation for wanting to pair things with this validation server, so you could have some way of confirming if you've got like, if you chose the bad analysis or the good analysis. I'd love to hear everyone else's responses though.
Yeah, do you have, can you give users an idea of the types of analyses that they can do without validation? It sounds like you're a ways away from a validation server.
For things like summary statistics and microsimulation, it's worked very well. Just for like normal multiple linear regression, it works pretty well. But if you start doing things where you're interested in like discontinuities, our methodology is intentionally trying to blur things. And so those types of methods don't work very well, which is problematic because that's what a lot of tax analysis is based on. So we're highly motivated to get the validation server to work well.
Right. Are the synthetic data available?
So for people who have access to the PUF right now, and that's not everyone, they can have access to the supplemental SynPUF. For the bigger, more complicated file, no, that's still a work in progress.
I see. Actually, Brett, you also, maybe I missed it, is the synthetic data is there a product that's actually available?
That's a great question. So technically the terms of the DUA prevent us from doing that. So it's a proof of concept now, and we're allowed to make the code and the neural network weights and all of that available. So that's what we've had to do so far. But again, sort of motivating factors for why these types of things are really necessary, because some of the DUAs are fairly restrictive.
Yeah, I guess that's a whole separate challenge and an obstacle there. To practical application.
Can I ask a quick follow-up on that? Is that okay?
Yeah.
So, you haven't released it, but one thing you didn't talk about is like how to determine the budget. Like, did you evaluate your methods at different values of epsilon? And if you were to release the data, how would you go around maybe picking the optimal epsilon?
Exactly, and that's I think a core challenge. And there's a group at Harvard now, since they had to work move there, who have a paper on this honestly, I think this is one of the biggest challenges of differential privacy and sort of the methods that we've done, which are explaining what the privacy budget means to somebody who's non-technical, and how are you actually putting that into a legal agreement where you are asking people to accept some level of risk. And so in our case, we showed it at a variety of privacy budgets, and largely based it off of the original deep learning with differential privacy work. I'm forgetting who the primary author was from that off the top of my head, but so it's really a scale of showing sort of the different parameter options there, and what was sort of the lowest budget that we could generate realistic seeming data for the correlation structure analyses and for the machine learning tasks. We obviously couldn't repeat the clinician actually reviewing the data manually for all the different parameters, but yeah, so it's a start there. And I think that translation of this epsilon delta differential privacy value to a legal agreement is one that is really key, and I think it's stopped a number of projects from progressing in different areas in the space. So I think it's really important to get that right, and not sort of do I've seen a lot of companies do the hand wavy approach of your data are now de-identified in private and there's no risk. I think there's an educational process that needs to be available to privacy attorneys and everybody else.
Thank you.
Monica, can you elaborate on measuring the variances and ensuring the synthetic data is able to capture the modeling effect?
Yeah, sure. And I think I'm sure also Brett and Erin has experience as well. So whenever we're doing multiple synthetic data sets, we do that first of all to capture the variability, because every time, especially from a Bayesian model at a particular Markov chain Monte Carlo iteration, if you only choose that one, it might be different from a few others, right? So we do that multiple times. But to answer, I guess, that particular question of how to quantify that and measure that, the thing is, for any kind of utility, especially analysis specifically, they're the one that I show, like point estimates, as well as the confidence intervals, and I think Erin showed a little bit as well in his talk, is that there are certain combining rules that people can use to come up with valid inference from multiple synthetic data sets. So it is actually, and Saki is an expert on that as well, stemming from missing data imputation literature and then adapted to synthetic data literature, because multiple imputation also requires multiple imputed data sets and trying to come up with valid inferences. So I guess that would be my short answer. I'll happy to drop in some kind of references for those papers when they talk about how those combining rules work. I can do that afterwards.
Okay, great. Erin, is it good that you were not able to get good results for those very sparse variables? I assume they pose a higher risk of being a disclosure risk.
Yeah, I think that's right. Yes.
And for Brett, did you end up extending to categorical variables with your private GANs work?
So in our data, we were able to basically one-hot encode anything that needed to be at that stage, because we weren't dealing with sort of high-dimensional categorical data. There have been a number of methods since that have, I think, dealt with mixed data types in more creative ways than we sort of did in our work. And so I'd refer to some of those examples, and I'll try to post a link in the Q&A if I can just look up one or two of the papers.
Yeah, if you want to add any links to your slides before we post them, you're welcome to do that as well. Last question for Monica. Have you explored how feasible it is to use apparent matches between real and synthetic data records according to quasi-identifiers to infer anything with any confidence about the real individuals? For example, if a synthetic record with 20 variables uniquely matches some real record on 5 quasi-identifiers, but differs on the majority of the remaining variables, then the matching the synthetic record with the real record still doesn't let the attacker have much confidence that they can infer anything about a real person.
Yeah, thank you, Christine, for the question. Yeah, I personally have not explored that, but I totally see the point. And I think a lot of times this is why I guess differential privacy is getting more popular. And then, because for synthetic data, usually, and I guess typically whatever kind of risk you're evaluating, like the one that we use is identification, but there's also what we call attribute disclosure, learning about the sensitive values, as well as inferential disclosures and all that. All of them, one way or another, will require some kind of assumptions of what the intruder know. So that is always a limit, I think, a limitation in terms of all of these methods. But specifically for what you describe, I agree. Even though we can assume certain variables to be known and then use those to be matching, and then we can come up with a probability statement of how likely it is. But in practice, I think it does require more work to actually dive into a little bit more of, yes, you can have, let's just say, a 0.9 probability of guessing this person correctly, but in practice, does that really translate into finding that person 90% of the time you do that? I don't think it is that understanding of the probability itself, but I would say that it's definitely an important and open-ended research area.
Okay, great. So there are a few other questions. Well, the rest of the questions have been answered in the Q&A text. Rick, is that something we can export and we can just add that to the slides and the recording information on our website?
Yes, I can do that for you.
Great. Brilliantly, it is exactly 1 o'clock. So thank you all again thanks the speakers for presenting, and thank everyone else for attending and for all the great questions. Have a great afternoon.
Thank you.
Thank you, everyone.
Thank you,
Thank you,
everyone.
Bye.
I'll be ending this session now. Everyone enjoy the rest of your day and have a great weekend. Bye now.
Thank you, everyone. Bye-bye.
Bye.